Okay. Okay. Das mal schön. So, schiebe das mal weg. Okay. So welcome to the second lecture of mathematical or in mathematical finance. So same style as last time. So along the way, I might try out new things, but for the moment, I think this is a good style to do the lecture. And as already said, well, please feel free to write me back feedback anytime so that I can improve the style of the lecture. So if you think there are improvements or possible improvements, just let me know. So first thing we want to do is we want to recall what we have done last lecture. So first thing is, well, we introduced two classes of assets. And these are the class of assets we want like to consider throughout the course. The first one is the risk-free asset. So this was our bond market or bank account. So this is a class of asset in which you can invest basically without risk, because we assume that this is a deterministic process. And this means in financial terms that at time zero, we know how this process will evolve over time. Missing something. Sorry, learning to write here. So at time zero, we know how the process will evolve over time up to time terminal t. So a priori, we know at today, if we invest in this asset, how much money we will make or lose over our time horizon of 0 to t. And as before, time is in this course discrete, so t involves my, let's say, natural numbers from 0 to t. But of course, you could do relabeling and say this is actually microseconds and not days or years. And the second class of assets, I mean, this is the most important one for the course, are the risky assets. So these are the assets. So we have a stock market, shares of companies which have prices, and these prices are denoted by S1 to SD, and they again involve in time. So the price at time zero reflects usually the current price, and then let's say tomorrow the price at t equal 1 is represented by random variables, because a priori we cannot forecast the future prices. So this is why we want to model this by a stochastic process, and we will make this more rigorous later on, but this just means that the sequence of prices are just random variables. So you have a sequence of random variables which are labeled by time. This is then a stochastic process again. Okay, so this is make. These are the two. So actually, our market it consists of D+1 asset. Oh, why is this not? All right. All right. So what does it mean? Here we have a financial market denoted by B and S. This is just the short writing for, okay, we have a discrete time market consisting of D+1 assets. T is our financial market, or more precisely, it is the model for a financial market we are considering. And then if D is equal to 1, this is what we are doing today. This market here is called one-dimensional. So basically, the dimension of the market we are considering is determined by the number of risky assets. So we always assume that there's this risk-free asset, and then D. This is market. With D risky assets. Sorry. So this is what we motivated last time. And now for today, what do we want to do? So today we want to assume actually that we work on a one-dimensional market, and the market fulfills for us the no arbitrage principles. Right? These are the underlying principles we assume throughout the whole course. So what does it mean? Just to verbally recall it. So the market is, first of all, arbitrage free. So there's no way to make money without any risk. And the information is fully reflected by the prices. So the efficient market hypothesis. We have a linear market, and we have a linear market with a linear pricing group. Sorry. Okay. Okay. This is what we face, and now we had a third class of financial objects we wanted to consider. Which you haven't modeled yet. And this is the class of financial derivatives. So these are some, mathematically speaking, function acting on the underlying price processes here. Okay. So what is a financial derivative? I mean, you can make this, the moment we have set up a probabilistic model, we can make this mathematically more rigorous. But as I motivated already last time, I would like to start with some general abstract definition, which are mathematically maybe not so rigorous as you expect them, but the concepts we are developing today and have developed last time, I mean, they're generally considered in different class of models, but the ideas and the concepts are the same. These are derivatives. And I mean, there are several names which you might see in the literature, so let me recall them all for you. So these are, I mean, of course, the shortcut of financial derivative is just derivatives, which should not be confused with the derivatives you know from your analysis courses. And you can also call it contingent claim or just claims. So this is, we were just a contract. Those cash flow depends, it should be, depends on the future values of, that's ST, so for a risky asset. Oh, why can I not write there? Sorry. Oh, okay. cannot. Yeah. Sorry. So that's. So what does it mean? This means, so this is a lot of words. Means, I mean, they are not basically our primary asset which we put in there, and they are modeled by us. They are somehow functions acting on the future prices. So we agree today on a certain payoff, some counterparty is like delivering us, depending on the future values of our underlying financial market. So mathematically speaking, as I already said, this is sometimes even easier to formulate. It's just saying, okay, I have a function or functional, because it might depend on the whole trajectory of the prices, mapping to the real numbers. Okay. But canonically speaking, these are contracts, of course, some agreements. Yeah, how we exchange in the future some cash or the asset itself. Okay, so let us consider some simple examples, and then, I mean, later in the course, but not today, we will go consider even more complex ones. But I think it's good to have first example in mind before going to abstract mathematical theory. So today, it will be again a rather relaxed lecture. From next week on, we start doing what I would call proper mathematics. So what is it? So the first thing is, I mean, maybe the most, I mean, structurally most simple one are so-called forward and future contracts. This is definition 1.1. All right. So, I mean, just to, let me first write the definition. So what is it? Sorry. Forward contract is agreement between two parties. This is, right, we have, as usual, our market consists of, let's say, a buyer and a seller. So otherwise, I mean, there's no trading going on. So we need always a buyer and a trade and the seller. But I mean, this is what we anyway assume. So we have a liquid market. So this always exists. And so we agree on at time S to buy or sell a given asset. So we agree what asset it will be for a fixed price. So we agree at time S to trade the asset for the price, which is as T. So T is, of course, a future price. Okay. And just to recall it here, so S and T, of course, we are only considering times in our index set. This was the set 0 to T. Okay. Right, so at time S, we agree to exchange the asset for a price which we agree on at time S. And entering such a contract is for free. So there's no cost or transaction cost of entering this type of contract. Just change it. I have green. So what? Oh, so just to pointed out. So of course, this is, basically included in the definition. Cost of entering the agreement is 0. Okay, and now we recall that we said last time, okay, we always want to assume that our market fulfilled the no arbitrage principles. And this has certain consequences for the prices of such financial derivatives, and in particular for the prices of forward and future contracts. So because the prices and of derivatives and so on, they are hopefully determined by the underlying financial market. And the reason why we can hope for this is because the payoffs are not independent of the underlying market, they are just functions of them. So this is why we have the hope that in the end, all we need to forecast or determine about financial derivatives can be done by our underlying model. And the first simple property here is lemma 1.2, which tells us if we are on such a market fulfilling the no arbitrage principle, then actually we know that this forward price FST is uniquely determined by the underlying market. So forward price as T, so this is the price at time T, the price at time S, we agree on to sell or buy an asset at time T is given I. So this is ST is equal to S, so the current price of the risky asset, and for the moment there's only one risky asset on the market, so this is the one risky asset, and then multiply it with BT divided by BS or S. Okay. Just me briefly check the questions in the chat. No. Okay. So you see, in this market, which fulfills the no arbitrage principle, here the forward price, which is not the actual price of entering the contract, it's the price of we agree on in this agreement, is fully determined by our underlying market without assuming any sophisticated probabilistic underlying model. So let us start with some first simple proof, which is done by contra positive, right? So we want to assume that this equality here is not true, and then derive that the no arbitrage principles are also not fulfilled. So first case, first case is we assume that the forward price is strictly less than S multiplied with BT divided by BS. Okay. And assuming so, we want to construct an arbitrage of it. So how do we trade to get an arbitrage? So some trading strategy which zero initial cost and with a certain, certainly a positive payoff, or at least a non-negative one. So what we want to do at time S. And the obvious ideas, of course, in this, as we see in a few minutes, will work is to buy the cheaper one and to sell the more expensive position, based on this assumption we have here. So what do? So we enter the forward contract on the long side. So what does it mean here? Long side means we have we have to buy the asset at time terminal t for the price st. Okay. This is a contract which we can enter for 0 cost. So this was free. Oh, and now we sell the asset. Risky asset. We sell exactly 1 because we have the right to buy exactly 1. And this cost us SS, right? So this is at time S, the price of the risky asset is SS. So if you buy 1, we have to pay for it exactly SS. And now we put the money we got, because we sold the asset, so we got some money, or maybe a negative amount, but it's not important here. So we put this in our bank account. Right. So you see already here, there are a lot of assumptions in it, which we put in our underlying market, right? So we can always buy and sell. We have no liquidity risk. We can short sell. So we can sell an asset which we actually don't have to get a negative position. So there are several strong assumptions by saying this is the right forward price, or to get this proof done. So what are the costs of doing so at time 0? So our costs are 0. Why? Because we're entering the contract costs you nothing. Selling the asset means minus S. And for selling it, you get the money, and this amount you get is SS. And now you put it in the bank account. So you see this is just 0. Now you put it in the bank account, so you buy the bonds for the price S, and this means you divide by S to get the number of bonds you can afford for the price S. Yeah. These are ways. I need a new page. Okay. Right. Okay, new page. And this is, so we basically started with 0 capital. Not even only basically, we started with 0 capital, and we implemented now this trading strategy at time S. And now we want to see what happened at time T. Right. Okay, what? All right. So what we do, and okay, we agreed on a forward contract. So we have to settle our forward contract. So this means we have to buy one of the assets, which erases or like canceled out our negative position in the risky asset. So this means we end up with some profit, which is, so what is our profit? So we have to buy the asset for the agreed price, which is FST. So we have minus FST. Sorry. Well, we sold one asset and we bought one, so we have 0 assets. And now we have the price of the bank account, or the evolution of the bank account moved. So we have here now SS divided by BS multiplied with B at the time t. And well, so that's let me rewrite this in the following way here. And now you look at our assumption, which is right at the top here. So what you see is that this is a positive number, if I haven't done any mistakes. Right? So you see, this is, I mean, my assumption. So my assumption. So what is it? Hence, we created an arbitrage, right? So just, I mean, to recall it, what this was arbitrage. So we started with 0. So we started here with 0 initial capital. And at the end, we always have a strictly positive amount of money if we assume that the forward price is strictly less than here the right-hand side, the top line. Okay. Great. All right. But of course, there's a second case, because we wanted to assume that here we have, sorry, in our, we wanted to show that here we have an inequality. This means, sorry, we have 2 sides of inequalities. So what do you want here? So we need to consider the second case as well, which works pretty much the same as the first case. So what we do is we suppose that now the forward price is strictly bigger than our right-hand side. So that's, we want to assume, and we want again to create some arbitrage. So let me be a bit quicker here. So at time s, okay, let me try it out. So if someone is brave enough to explain me how I want to trade. Do I have sound? Yeah, I have sound. So please just, I mean, if someone wants to explain me what I have to do now to create an arbitrage, please just speak up. I mean, I want to have a live lecture to get some interaction, so let's try this. Okay, then let me, I mean, maybe it's too simple. So obviously, again, you want to enter the contract, the forward contract, on the favorable side for you. So you enter the forward now on the short side. So you mean you have the right to sell the asset at the future time for the pre-agreed price, you buy one risky asset for SS, and again you put the amount which you got from buying the asset, which is now -1 because you spent -1 to get the asset, so you have a negative amount usually in your bank account, even if you have not assumed yet that the prices are negative or positive. So in principle, these prices could be all negative, but I think it's natural to think of positive prices. So it means if you buy an asset, you have then on your balance sheet also some negative position, which is in your bank account. Okay, again, the costs are 0 to do this. Are 0. Right, entering the contract is again for free. This costs you, so this is the amount you have in the risky asset, because you have one risky asset which has the value as S, and now the money you spend on this is what you put in the bank account. So you have this amount in the bank account, which is as 0. And now at time t, where the contract is due to, you settle again your contract to make some money. For profit, which is this is what you have then, because you get the money, you lose your asset because you have to deliver the asset for the price as FST, and still you have the gain you made in time S, you have it in your bank account. So you have there is for the loss, right? So that's what you end up, and now this is by assumption a positive amount, right? And again, this means arbitrage, which we wanted to exclude, but by our no arbitrage principle. So that's the end of the proof. Okay. So why are such forward contracts traded? Or someone agrees on these forward contracts. There are two, traditional reasons for it. The first one is hedging. There's no number. So the first one is hedging. So this means here risk reduction. So this type of forward contract appeared first in agriculture, where, for example, farmers wanted to hedge themselves against the risk of future price fluctuation. So if you're a farmer and you want to produce, for example, potatoes, you want to make sure that you can sell in 1 year from now the potatoes for a sustainable price. And of course, depending on weather and so on, the prices might change. So what you want to reduce your risk of losing a lot of money, you want to agree now on a price for which you can sell your potatoes in 1 year. At least a certain percentage of your harvest should be then be sold for this price. Right? So this is why, there's a good reason to set up these things. Also if you produce cars or computers and whatsoever, you want to have, you need to have some pre-products, and you want to make sure that these pre-products get delivered on a pre-agreed price so that you can, I mean, have less risk of price changes. And the other thing is, it's probably a more modern perspective, is speculation. So there are many goods, the commodities and so on, which we talk to, like oil and other goods which have storage costs. They might be hard to trade for you because, well, you have a lot of cost of storing, delivering them, and so on. So you might want still to trade them because you might have a good insight about these markets, but you don't want actually to get these goods, or at least not actually to get the goods now. You might want to have the goods only if you immediately can resell them in, let's say, 1 year from now. So this is the second thing. You might want to use these forward contracts to trade on things which you cannot actually deliver or don't want to have physically. Second remark, because I'm already mentioned on the headline here. So what are future contracts? If these agreements, these forward contracts, are traded on, for example, an exchange, so then you have basically a day-to-day evaluation of the prices, then they are called futures. Are known as futures. Future contracts. Okay. So this is basically the same, except that, well, these are then traded objects on a exchange, and then you usually have a dealer or broker who takes care that they're marked day from day. So you want to make sure that because if the underlying price is fluctuating, of course, the correct price of the forward contract has also to fluctuate. I mean, look at the formula we just derived. So basically the losses and profit you make from day to day is put in some account. And this means you can also resell these forward contracts and so on this exchange market to other participants. But mathematically speaking, they are very similar because, well, I mean, the style of the agreement is in the end the same. Okay. So these are forward contracts and futures where one basically pre-agrees on a certain transaction. So there's no option payoff involved whatsoever. And this brings us to the next chapter, not chapter, subsection, which are options. So there you get the right to buy and sell things without having any obligations if you're the holder. Okay. So I'm not running through all the potential derivatives on the market, but I want to give you some of the most frequently observed or traded ones. This is first put and call options. So I mean, you can look them up. Basically, they're really high frequent, really heavily traded. So you can basically look on your favorite financial website and see how the prices look like currently acting on different classes of assets or different stocks of companies. Right. So what is a call option? Call, short, also called just without the option. So a call option is a contract which gives holder the right to buy asset. Asset mean here the risky one, because we have one asset, so this is the risky asset, asset for fixed strike price. So this is just a constant here. Oh, can I write that? Okay. Right. So what we do is, right, this is a type of contract. If you have it, you have the right at usually some future time to buy the underlying risky asset for a pre-agreed price, which is called strike price K. So K is just a constant which we agree today, and for which I, as a holder, have the right to buy the asset. You see, this is different from the forward contract where we have to trade the asset. Here I have the right, but no obligation to buy the underlying asset. So if I want and the prices are good for me, I will buy it. Otherwise, I will just drop the option and say, I don't want to have it, I pay nothing. And there are different rights to exercise these options. So if I enter this option, then it means I exercise it. So there are two styles. The one is European. Maybe I should use colors I have here. So European version of it. If the holder can exercise, and this means to use it, the option at the maturity. So there's a terminal time called, let's say here, capital T. So I mean, in our model, it makes sense. You always use the terminal time and stop modeling afterwards. So we can exercise the option only at the terminal time. And this means we can only buy the asset at the terminal time for this pre-agreed strike price. Right, so this is okay. Oh, sorry, where is? Wait, what happened? Wait. There we are. Maybe I should save. Sorry, let me briefly save because I was scared that I lose now all the files. Where is it? My files, lecture. Save. Sorry. Okay. And now, second style is American. I mean, these are the two. I mean, there's also other styles of option of or exercise rights in the real world, but these are the two ones we are considering during the course. Of one is European, the other is American. And American means you can, the holder can exercise the option at any time. So any time means, of course, only in our index set T, small t in. Right. So, I mean, you see, I mean, basically they're the same option, but American call option, European option are like distinguish each other in the style of exercise rights of the holder of the option. And the second thing we observe, which is different from the forward contract, is of course they have a positive value even at the time where we want to trade them, because they basically, I mean, there's an asymmetry between the rights the buyer and the holder has. Sorry, the buyer and the seller has, right? The buyer has the right to exercise the contract if it's favorable for him or her, while the seller of the asset, of the option, has to deliver the, well, whenever the holder wants to exercise. Right. So let me put this in a mathematical way. So what is the payoff function? Oh. What is the payoff function of a European call option? Option at terminal time t. Right. And again, if you open probably the most mathematical finance book, what you will see is, well, what is it? The payoff here is nothing else than the positive part of S, so the price at time terminal t minus strike price, and then the positive part. So this is a standard notation I will use rather often throughout the course. That's positive part. Right. So now you say, okay, this is mathematically speaking rather simple, right? This is just a convex function acting on the underlying price process. So that's nice. But again, and this is what I somehow want to make you aware of, is that the payoff function looks like it does here is really because there are the no arbitrage principle in order. Because we assume that we have here somehow a rational trader who will only exercise the option if it's favorable for him or her. So if the price of the underlying process here as at time capital T is bigger, strictly bigger than the strike price, then it makes sense for you to exercise the option because you make some profit. For profit. And the profit is, of course, here the positive one. And I mean, why do you want to exit? Because also you have a liquid market. So even if you don't want to have the asset at the time terminal T, you would still buy it and immediately resell it because there's a liquid market, you can do it to get at least a profit. So if you drop this assumption, for example, of a liquid market, even if the option is favorable, the market is favorable for you, you might not be willing to exercise the option because you cannot resell the asset you have then. So by writing down this little cute formula for the payoff, we actually use almost all the assumption we agreed on last time. So you let it lapse. So you will not exercise it. Because then it's unfavorable for you. Why should you take a loss which you don't have to take? Sorry. Okay, I need another page. Okay, just briefly to give you, so the first week is a lot of language, but then afterwards we will use it throughout the course. So even if you think, oh, there's a lot of vocabulary currently, don't worry. I mean, all these things will appear again, and then you will slowly get familiar with these. Let me, because I think it's good to. So what is the payoff here? Let me try to draw a picture. So, right, so here you have the payoff at time t. This is the price in this direction. And now, how does my payoff looks like? So wait, I have here so this is actually one line here. So you have zero payoff up to the amount that the asset price is less than the strike price. So this is the second condition we have here. And then afterwards, what do you see here? We have a linear payoff function. So afterwards, it's just linear functions from here on, more or less linear. You have the payoff. Okay. Just to fix some language, as I already started to do. Okay. So call option is set to be in the money. I mean, these sayings are pretty much self-explaining, right? So you're in the money if at time t, so this is, I mean, a saying you have at any time t in our index set. So the moment there would be a positive payoff, you are in the money. And that was not as planned. Okay. And you are out of the money if, of course, the price is less than the strike price. And finally, you're at the money if the strike price is equal to the price, current price. Okay. This is just, if you want to do an internship somewhere in a bank, you might see these sayings. All right. So another option, which is the counterpart somehow of the call option, is the put options. Okay. All right. This is definition 1.4. Didn't work. Okay, so put option is a contract which gives the holder the right to, now it's not buy, it's sell the asset for a strike price. Okay. Okay, so this is basically very similar to call option, but except that you have the right to buy the option, you have now the right to sell the option. So this, I mean, sorry. Okay. Again, I mean, as for the call options, you have in the money, at the money, out of the money. You have the European and the American style options as well. So all these vocabulary transferred exactly in the expected way to the put options. So let me just draw you the picture for the payoff functions, and there's no, I mean, no need to go through all the words again. Payoff of European put. So what is it? Oh. This is now positive part of K minus T. Why? Again, these are no arbitrage principle, ensuring that this payoff will look like this. So we exercise if the option is favorable for us. This means price is strictly favorable for us. So if we can sell the option now for a price K, which is higher than the market price ST, right? Then we exercise the option. Otherwise, we would sell it on the market itself and just lapse the option. And this is the second case. We lapse, so this means we are just basically throwing away our right to sell the option if there's no need. Again, what do we call? Oh, sorry. Okay, let's draw a picture. One straw. So what is it? So again, we have the payoff and the price as the coordinate axis. So that's the payoff at time t. Here's the price. That's the ST. And here's somewhere the strike price. Okay. So now, well, we will, that's not a good idea. We will use the option if the mark price is less than the strike price K, because then it's favorable for us to exercise the option. And afterwards, we will not use it. So this is 0. Okay. So why do I want to use options? I mean, the purpose is pretty much the same, I mean, ideas than for the forward contracts. So again, it's hedging. Right? We can hedge ourselves against future price changes. So this is again risk minimization and risk reduction. And right. Okay. Right. So if we face the risk that the prices in the future might move unfavorable for us, and we want to produce based on some goods, we want to maybe buy a certain amount of put and call options to hedge against unfavorable price movements for us. And the second reason is speculation. So if you consider, for example, now here the payoff profile of the put option, right? You could speculate now on falling prices. So you buy a put option and this put option gets into the money if the prices are dropping. And well, the reverse perspective, the call options up here. So here's you bet on rising prices. So you say, well, I believe that in 1 year from now, the price will be much higher. And this is captured by the payoff of the call option, where you have no risk of losing any money, except of course the initial price you pay to get this option. Okay. Okay, now this is okay. Let went first, so later. So I'm not going through more examples. So option, more complex payoffs are called exotic options. Right. So basically, everything which has a complex payoff profile are the so-called exotic options. But this is, I mean, for the beginning, not so important. Just if you see the word, exotic option refers just to a complex triad. So you have path-dependent options and so on. Currently, these call and put options, they act only on the underlying price at one single time. But of course, you could think about options which depend on the whole price trajectory of an underlying asset. And one main goal of the School of Mathematical Finance will be to understand how the right or correct prices or arbitrage-free prices of underlying of the such options, so the put and call option and also more exotic options look like, and how can we, as an investor or as a bank, hedge ourselves against the risk of selling an option. But for this, we will need to have, I mean, a bit more complex modeling. But what we can do already is to derive certain properties of the prices of option without specifying any further how our price dynamics of the risky asset actually looks like. And this is what I want to call model-free properties. And we actually have already seen one. So namely here, the lemma 1.2. So this one here. Which tells us that the forward price is basically determined already by the underlying market just by assuming the no arbitrage principle. So we did not write down any specific dynamics of the underlying prices. We just said the underlying market model has to fulfill our no arbitrage principles. And this is what I mean by model-free properties. It doesn't matter what specific model we will write down later on, as long as this model fulfills the no arbitrage principles, then these properties we derive here have to be fulfilled. So just to recall it, I mean, even if I said, so we have a one-dimensional market VS, which fulfills the no arbitrage principles. And again, to emphasize this, this means even if I'm not proving these properties again, they are true for any model we will write down throughout the course here. Okay, so let us try to understand a bit more the price of a put and call options. This is the context of lemma 1.5, which is the so-called put call parity. Sorry. Right. And what does state is, okay, I mean, assuming that our market fulfills the no arbitrage principles, then we have, let us first select CT, okay, we're talking about European options. So these are the price at time t. Right, the moment an option is traded on a financial market, it has also a price process associated to it, or value process, which means at every time t you can buy and sell this option for the price here CET and PET. Of European call and European put with strike K and maturity T. Right. Now you prove. So you see, I said I didn't write, sorry. Sorry, I forgot to write the statement. Then we see that the difference of the price, the European option, of the call option, and of the European put options are just given by the asset price and basically the forward contract strike price K, and this is so the proof is actually left to an exercise. So this is on the new sheet. You are invited to prove this. But since I have a bit of time, so what you, I mean, why you see, can see that this is actually rather natural property is look at the payoff at time t, right? So this is where the payoff function is actually the price, and now you draw yourself a picture. Again, this is here payoff, and this is the current price, the price at time t. Here's my strike price. So what do I have here at the terminal time? Right, I have my call option. Oh, sorry. I have my call option. I mean, you remember this is the payoff function of my call option. And now I have minus my, so this is call. And now I have here my minus put option, right? Where is there? So that's minus put, and then you can see if you this is minus put, that is call, and now you see that this is exactly the picture you get from the right hand side as well if you draw this at the terminal time, right? This is just ST, right? Here's ST minus K. So, I mean, I'm leaving you to like making the proof properly. On the next exercise sheet, just that you're aware, I mean, well, just to convince you that this is the right claim. So, okay. Okay, this is not a proper proof, so let's make here quotation marks around it. Okay, one final a property which you might have seen already in some like economy courses or a course in the business department is what you always can say about the prices. It's another model-free property. This is lemma 1.6, which tells you the law of one price. So if there are two payoffs which have exactly the same payoff at the terminal time t, then they have to have the same price at the current time. Law one price. So again, assuming our no arbitrage principles, and you again basically need them almost all to prove this, is that if you have two claims, psi 1 and psi 2, which are supposed to provide the same payoff, at maturity t, then the price of 1 and 2 has to, so price means here at t equal, at any time. That has to be the same. Right? Okay. I mean, this is pretty obvious, I guess. Because what you would do if the price is different, and this is what I can do in the next couple of minutes, very briefly again, is, well, if the price is different, then you would buy the cheaper one, sell the more expensive one, and make some profit of it. Mathematically, one again has to, of course, everything in math, one has to prove it, and same idea as before. So we want to run a proof by contrapositive, meaning we assume that the prices are unequal, and then we want to contradict it by saying that then there's an arbitrage on the market. So let C1, P, C1 and PT, C2 be the price at T of the claim C1 and C2 as respectively. Okay, it's just to fix some notation. And now I'm just doing the first case, and you know how to do the second one, I guess, by now. Right, so what we assume is to make our contrapositive work, we assume that the price at time t of the first payoff is less or equal than the price at time t of the second one. Right? And now you implement the obvious trading strategy. So at time t, where you have this inequality, or where we assume you have this inequality, you buy like 1 for the price, and you sell side 2, and you see again we assume here already that we have an that we have a liquid market, because otherwise it might be not possible to do so. But here we have always, for every buyer there's a seller, and the other way around. And what this transaction creates amount of money, and this amount of money is given by obviously the price of the second payoff minus the price of the first payoff, which is a positive amount, and this is put in the bank account. Okay. Okay, first what we need to ensure is that this leads to zero cost. So again, what are the costs of this trading strategy at the time t? Well, obviously, if we buy, we lose some money. If we sell, we get it. Okay. And now we wanted to put the difference of these two prices in our bank account. So that's what we're doing here. Ooh, maybe I should. Right, so that's the amount we can put in our bank account, and this means we have to divide it by the price we have to pay at time t, and this is the amount we get then. All right, simple. And now we hopefully in the page. What happens at the terminal time? Well, obviously, because there's the payoffs of side 1 and side 2 cancel out, right? They're the same. So if we hold one and the issue of the other one, our cost with phase are 0 at this time, so this cancel out. And we obtain profit, well, what we put in our bank account, right? So that's the number of bonds we hold. So psi2 minus psi1 divided by BT. And recall, I mean, this is always, I mean, the price evolution in the bank account is always strictly positive, so we have no issue of swapping signs here. So you see, again, we found a smart way to create some arbitrage. So arbitrage, which contradicts our no arbitrage principles. Right. Second case. Right there. Second case works the same. Okay, wait, let me make my note complete. Don't worry, I'm not writing the whole second case. So the second case is assume that now the other inequality holds, and then works. Then arbitrage. Right, you make the same, you just swap all your positions. So I'm not doing it again, so I don't want to bore you. All right, we're coming to an end. So what you see is, I mean, even without any specific model, this is why I refer to this as model-free properties, we can derive some properties of the prices of assets, of financial derivatives. But in order to have some more specific properties, like really, okay, to determine some prices, we need to develop a more sophisticated theory. And this is what we start next week. So next week are heuristic processes in discrete time. And well, what do we have to learn? First, we have to somehow understand how the information flow works, with the generation flow generated by the enterprise process. We need to understand a bit better the concept of conditional expectation. So how can we take the expectation of some future payoffs given the information up to time t? And we need to understand what are the good heuristic processes which we want to use for model financial markets. And here the notion of martingales will come into play, which are somehow a way to describe fair games. Since I started a bit late, let me at least recall some things you might have seen already. So I hope you're all familiar with the Borel sigma algebra. I mean, this object will be used from next. So this is for me to fix notation. So I hope you know what it is. I mean, I'm pretty sure you know what it is, but I'm not sure if I follow exactly the same notation as in the course before. So the LP spaces, so the Lebesgue spaces as usual. Here, if I'm not specifying it, this means on our underlying probability space. On the Lebesgue spaces, And I mean, if you feel like you need to recall it, you can look at the appendix and the lecture notes. There I put some essentials to make sure that you have, make sure that you're aware what we need further. And then if we have now a sequence of random variables, n in n, the smallest sigma algebra generated by these random variables, usually start with 0, so let's start also with 0, is denoted by, so this sigma 0 to n, and this is by definition just the sigma algebra generated by the pre-images of these random variables. So here A is coming from the Borel sigma algebra, and I is coming from our index set 0 to n. Right? So I hope this is not new for you, but I mean, if you think you need to recall it a bit to be prepared for next week, please do so that we are not getting lost next week. All right. Thank you very much. And well, hopefully you enjoy the current exercise sheet, which is due to you on tomorrow. And otherwise, I wish you a nice day. Thank you.